Good afternoon, I am Mr. Ish. You're joining me here for a practice video here. We're looking at some questions on type 1 improper integrals. The video directly prior to this where we were talking about some of the theory behind these type 1 integrals. Keep whatever you've seen in that video and bear it in mind as we go through these questions. When we're looking over here, we're seeing an instance over here of an infinite interval coming into play. We're also seeing something over here which looks very well like an arctan. An inverse tan antiderivative will be coming out of that. If you cannot see that, you have to learn how to do these type of integrals very quickly. Let's just look at this and then we'll get into the actual question, because you have to still get the antiderivative of this to do the question. When you're seeing this, you're basically looking here at an evaluation question. We'll be looking at a few of these. When you're looking at this, you got to be able to do it. You have to do some substitutions over here. X, you could also use trigonometric substitution integration technique, but I don't want to do that. If x is equal to root 5u, and then I know u is equal to x over root 5. You should also look at the video I've presented, the few videos on the arctan antiderivative and the related integrals. It tells you how to do these type of questions. And you're seeing this, then du is equal to 1 over root 5 dx, and dx is equal to root 5 du. You put all of this into play right over here. We're only doing the antiderivative right now. Then we look at everything else. 1 over x is equal to root 5u. Root 5u whole square plus 5. We know dx is equal to root 5 du. Root 5, and then you have du over 5u square plus 5. You can isolate a 5 over here. Root 5, and I've isolated this 5 and brought it outside the integral sign. I have a du over u square plus 1. This right here, 1 over 1 plus u square, or 1 over u square plus 1, is very well the arctan antiderivative. You know that's going to bring over here 1 over root 5, then arctan u, and then which is 1 over root 5 arctan, and what was u? It was this right here, x over root 5 plus c. But this right here is my antiderivative coming from this entire integrand, and we have to put this in mind because we will need it for this question. The video I presented on these arctan antiderivatives are easy, and they tell you how to do this type of question very quickly. You should be looking at this and just thinking of this right away without any of this work. Anyhow, let's look over here. We have to write this in our limit form. Limit as t approaches minus infinity. We're really looking at 0 to t, and then we have 1 over x squared plus 5 dx. Once we've done the antiderivative, this comes into the picture. And I'm going to bring this 1 over root 5 right outside the limit. Look, 1 over root 5, which is a coefficient, then limit as t approaches minus infinity. I have this arctan x over root 5, and all of this will be with regards to 0 and t. We have to evaluate this. Remember the whole concept about convergence and divergence. We'll present our answer such. When you're looking at the arctan, you can very well use a calculator, or you can use, if you want, the graph. The inverse tan looks something like this. Limit as x approaches 0, the function approaches 0. Limit as x approaches minus infinity, it approaches as minus pi over 2 as I'm told. Limit as x approaches positive infinity, your function will approach positive pi over 2 as I'm told. So keeping all of that in mind, and or you could have used a calculator. Let's finish this. We'll have to do this. 1 over root 5, we'll have upper limit, lower limit, and the difference of the two. We'll have arctan or inverse tan 0 minus arctan 0 over root 5 was just a 0. Here I have to put t in this place of x. T was minus infinity. Minus infinity over root 5. Minus infinity over root 5 is no different than you just saying minus infinity, right? Don't get lost in the semantics over here. That's all what it is. Let's evaluate this. You have 1 over root 5. Look at your graph over here for the inverse tangent function. Arctan 0, 0. Arctan minus infinity, minus pi over 2, right? You see that, right? If you don't see that, bring out the calculator. Write a number close to minus infinity. You can do 1 exponent 99. You see this minus 1 to the power 99? That's like a very large negative number. Inverse tan it, and you get minus 90, which is minus pi over 2. 0 minus minus pi over 2 is a positive pi over 2. Multiplying with this 1 over root 5, your answer will be pi over 2 root 5. What does this pi over 2 root 5 represent? It represents convergence, and it represents an area under the curve. For this function, if you were to graph it, you would have a clear finite area, and that's what it would be. And this question has been done. Again, I'm talking about the word convergence here because we have a function here for which the limit can be evaluated in the presence of an infinite interval. Imagine on your calculus exam, this was your question. You know, just by looking at this question, you would know and you would state within a single second that your answer is divergence. You cannot calculate an area for this function. The reason why you would do that in your mind, because in a matter of a nanosecond, you would think of this specific limit as x approaches infinity. You're thinking about a sine x function. What does it approach? You would say limit does not exist. The reason why limit does not exist, because you would think in your mind, you have a certain sine function which goes like this towards infinity, positive infinity. Forget the negative part. We're not looking at that. But you're seeing here in all instances this curve, your sine curve always oscillates between a positive one and a minus one. Always some value in terms of the output, which is your range, your y value is always somewhere between -1 and 1. When you're out here in the area of infinity, whatever that might be, you don't know where your curve was. Was it at -1? Was it at +1? Was it at any of these values in between in terms of the range? Because you don't have that clear answer here and you have this extreme ambiguity, you would have to say it does not exist. And you know, when we're talking about divergence, as I stated in the very first video on improper integrals, divergence exists when, with regards to the integral that you're trying to evaluate, with regards to the areas below the curves, a limit does not exist. Here I'm telling you beforehand, before the evaluation even begins, limit does not exist simply because of this aspect coming into play. But you're in your exam, you have to show why it does not exist, so we have to do some work over here. You will rewrite all of this as this limit as t approaches infinity. We're looking at 2 pi and t. We have sine theta d theta. Alright? You would do the antiderivative of this. And you would say limit as t approaches infinity, our antiderivative of sine theta is a minus cosine theta. And you'd be looking at everything here from a t to 2 pi, to which now you can then start doing your definite integration procedure. You'll have a minus, I'm just going to sit that outside, minus, I'll have a cosine of t, which is at infinity, minus cosine of 2 pi. I know minus cosine of 2 pi is a -1. I know this right here is an infinity because, as I've told you now, on your paper you'd explain why limit as x approaches infinity, cosine theta, you'd say limit does not exist because, again, cosine function runs between a -1 and +1 in terms of the output, the range, and at any point over here you don't know where your function is in terms of the output. It could be any value here in between, and then here all of this will end up giving you a minus infinity, and you would say your evaluation leads you to conclude that this function has an infinite possible area, and we're looking here at a divergence. There's no clean or clear finite area developing with regards to this interval over here. We'll let this be our last question for this video, because before I close this video I want to do a short or a quick forward in terms of what we can expect with type 2 improper integrals. It won't be anything too hard or crazy, just a quick introduction to that. We're looking here at a clear case of infinite intervals. You know you want to do a setup over here with regards to limits. Limit as t approaches minus infinity. We will do a distinction over here. If we're looking at a domain from minus infinity to infinity, we want to squeeze in a 0 and separate the intervals among two limits. So we can do here from t to 0, and we'll write everything as we see it, but going directly to the limit part of this entire question. And then here, you know, you do a limit, t approaches infinity, you go here from 0 and you put infinity here, but we're going to skip the step, as you know, and we'll just put directly t over here, and we have 2 minus x to the 4 dx. Everything here is polynomial, so the integration or the antiderivatives are easy. 2 comes out as a 2x, x to the 4 comes out x to the 5 over 5. You know everything here, you're looking from 0 up to t. Looking from 0 and t to 0, as you want to say, lower limit, upper limit. You have this little limit sitting outside, limit as t approaches minus infinity, and then we have this plus sign. Remember, these intervals are always cumulative, hence you have a plus sign. Limit as t approaches positive infinity, we have again the same antiderivative coming out. When you're looking at something like this with a lot of infinities coming into play, don't take things for granted, just work them out. Upper limit, lower limit in each of the places of x and the difference of the two. We look right here first. When we have 2, we're putting a 0 and we're putting a minus and then a minus infinity. This minus comes from the difference of the upper and the lower limit. Minus 0 to the power of 5 is just 0. Minus to a odd number exponent always retains its negative character. You'll have a minus, minus infinity. Putting over 5 is meaningless in the face of infinity because over 5 is too small and negligible to be put against an infinity. Plus, here we'll have a 2, infinity coming in here, infinity minus 0. Again, 2 is meaningless as well. Here we'll have infinity to the power of 5 minus 0 to the power of 5, which is 0, all over 5, but the over 5 is again meaningless. You see I'm skipping a bit of things over here, which is fine because against infinity these 5s and 2s don't mean much. Here we'll have 2 to the infinity. We won't skip too much though. Here we'll have a positive infinity, which will hit this will become a minus infinity. When we have this, we have a plus 2 infinity. When we see this, we have a minus infinity. We have 2 negative infinities, which can very well cancel against 2 positive infinities if there was such a thing as this, but we can assume there is. We end up seeing just as a net result a positive infinity. So the evaluation of this leads us to this answer, is that you cannot do a clear evaluation of this specific integral and its function over this infinite interval because of the concept of divergence. If you would try to do an area calculation with regards to what you're saying, you will have an infinite area and you couldn't calculate it. There's nothing finite. Limit evaluation here would tell you that we're looking at infinite over here in terms of our evaluation. Divergence means that there's a clear instance here where limits do not properly exist. And this question is completed. I want to end this video here on a few parting thoughts as we start thinking about type 2 integrals. Consider this, and we've already looked at this, 1 over x squared. We saw that the area, when we were doing the integration from 1 up to infinity, we knew that there was a good finite area that developed because this function zeroed out soon enough that from 1 up to infinity we had a good area develop, with the rest zeroing out mathematically, and you had convergence over here. Here we have an interval 1 and infinity. It stands out as being an infinite interval, but you can't always think of things like this in terms of absolutes or black or white. Think about the exact same case, 1 over x squared, and you know we can just do a little bit of a shifting here from 0 to 1. Now consider this specific situation over here, 0 but going up to 1, and you're trying to calculate the area of this. I'm not calculating it here right now, but maybe you'll have a divergence come into play over here, and then here part of the interval is no longer continuous. From 1 up to infinity we have a complete continuous interval from a to b. It's a continuous. But if this is our a and b right here, a and b, we're looking here from a to b, we no longer have continuity over this entire interval, because if you're seeing the domain of this is 0 comma infinity. 0 is not included in the domain. You will have a bit of a discontinuity involved over here, and here very well you might have divergence come into play. And this is where the situations of the type 2 improper integrals will come into play, where you have these jump discontinuities, or you have these discontinuities in your interval, and you may not even be looking at intervals here which have a black or white infinity in there. It's not clearly mentioned as infinity. You could have any finite number, but you might still end up seeing a discontinuity over there, and you might still end up experiencing divergence. Lastly, look at this function here, secant x. If you were to just graph it out, you know cosine x would be something like this. We're looking here only from a domain of minus pi over 2 to pi over 2. This right here is my cosine function. We have a vertical asymptote developed with regards to the secant function, and the secant function goes over here. Now if you're evaluating a integral such as secant x dx and you're trying to do area calculation from, let's say, minus pi over 3 to pi over 3, we have a clear continuous interval from minus pi over 3 to pi over 3. You'll have a clear area which you can establish, it's finite, and there'll be good value come out. But if supposedly you're looking here from the same function secant x but from 0 to pi over 2 dx, you're looking here now from 0 up to pi over 2, we know that this function will approach this vertical asymptote, and you may very likely experience divergence. Here the limit will very well be expressed because it's only one-sided. With regards to pi over 2, it's one-sided. Here your limit might very well be, let's use the notation t as it approaches pi over 2 but from the left. And you can see all of these specific peculiarities will come into play as you look at type 2 improper integrals. So don't always be looking for clear positive and minus infinities in terms of your intervals to start deciding whether it's improper or proper. You can very well have finite value in terms of intervals, but you may end up having an improper integral leading to a divergence. This right here from 0 to pi over 2 will be a very good clear case of divergence, because you're looking at everything here from secant x below that curve but this portion over here is going to keep going up towards infinity, and you'll have a divergence come in here, and we'll just use the letter D for divergence. So nothing is always black and white with regards to improper integrals. Nothing is always clearly delineated as positive or minus infinity. Sometimes you have finite values giving rise to improper integrals. With that, I will bear you all a good night for today. Thank you for watching my videos. Have a good day. Bye.